This crystal isn't made from atoms. It's entirely composed of electrons, no atomic structure, just pure charge. And it assembled itself spontaneously. At room temperature, a bizarre new magnetic material appears to flip between structured order and chaotic randomness. Imagine something that's simultaneously like frozen ice and raging fire. In a cutting-edge quantum lab, even time itself has begun to form patterns, almost as if it's solidifying all around the world. Physicists are encountering phenomena they never aimed to produce. These aren't just odd results. They're signs of completely unfamiliar forms of matter. And some of these findings weren't even supposed to happen. One scientist even said, "We thought it was a mistake." When Swastik Kar, a physicist from Northeastern University, first observed electrons aligning themselves into a flawless, crystalline pattern between two thin sheets of material, he questioned his equipment. His team reviewed the data multiple times, verifying it from different angles, before accepting what they were witnessing, something that goes against the conventional rules about how matter behaves. The discovery had no immediate explanation. Picture scientists running a standard experiment only to be interrupted by measurements that make no sense. That's what happened in Kar's lab in 2020. They were layering to ultra-thin materials bismuth, selenide, and a type of transition metal, dichalcogenide, when the data turned strange. Instead of scattering randomly, as electrons usually do, the particles arranged themselves into a flawless crystalline pattern, a lattice formed purely from electrons with no atoms involved. Naturally, the team suspected a malfunction. "We really thought something was wrong," Kar recalls. They reran the tests, recalibrated instruments, and triple-checked their analysis. But the result held. The electron crystal was real, and perhaps most astonishingly, it formed at room temperature. Typically, quantum effects like this require extreme cold near absolute zero where atoms barely move. Yet here, electrons self-organized into a crystal structure under everyday conditions, like those in your living room. After thorough confirmation, Kar and his team had to face what they had found. "It's tempting to call this a whole new phase of matter," he said. Let that sink in. "We're all taught the basic states, solid, liquid, gas, and maybe plasma. But this was a precisely geometric structure, not made from atoms or molecules, but from free-floating electrons arranging themselves into a pattern, as if electrons decided to start, obeying entirely new physical rules." But if that was surprising, what came next may force us to rethink the nature of matter itself. Imagine a material that's half solid and half fire-structured and chaotic, frozen and burning, all at once. That's exactly what researchers at Brookhaven National Laboratory stumbled upon in 2024 while studying a one-dimensional fairy magnet. "We observed something that should have been impossible," one scientist explained. The material displayed perfect magnetic alignment spins of electrons neatly ordered, like rows of soldiers. That was the ice part. But right next to it, electron spins were completely disordered, swirling in chaos. The fire. This wasn't a gradual change. The material sharply switched from one phase to the other along a clean boundary, creating a huge shift in magnetic entropy. That sudden change released or absorbed heat instantly, and unlike many strange quantum effects, this one has potential real-world applications. This sharp switching between states could transform refrigeration through magnetic cooling, a more efficient alternative to current technology. Even more exciting, these two distinct spin states could represent binary information, no south and one souths in future. Quantum memory systems. Understanding how these mixed spin states work could spark major progress in spintronics and quantum computing. One researcher remarked, "This unexpected result might form the basis of technologies we haven't even imagined yet." For generations, we've been taught that there are only a few states of matter: solid, liquid, gas, and maybe plasma. If you were lucky, your teacher mentioned the Bose-Einstein condensate. Fifth state confirmed in 1995. But what if that list is just the beginning? What if we're climbing a hidden ladder of exotic states, far beyond what's in the textbooks? We're seeing a surge of discoveries that don't fit the standard categories, said one physicist. Each one forces us to rethink what a state of matter really is. Take the supersolid, a material that's both stiff like a solid and flows without resistance like a superfluid. In 2024, researchers in Innsbruck, Austria, directly observed this behavior. Tiny vortices that only appear in superfluids emerged within a crystal, or consider time crystals. Unlike ordinary crystals that repeat patterns in space, time crystals repeat in time, forming structures in the fourth dimension. In 2021, teams at Stanford and Google used a quantum computer to create one. Then in 2025, researchers at Washington University developed a time quasicrystalline structure with temporal patterns that never exactly repeat. Then there's liquid glass, where particles move like in a fluid, but their orientations stay frozen. Or the Bose glass, where particles stubbornly stay in place despite quantum laws suggesting they should move. At the edge of all this is the Schirl-Bose liquid, a state marked by magnetically aligned currents arising from quantum frustration. These findings stretch our understanding of how matter can organize itself. So here's the question. Are we being too cautious about what we label as a state of matter? If these discoveries had occurred during the early days of quantum physics, in the early 1900s, would they already be accepted as official states? Or have we become so specialized that we hesitate to redraw the map? Even plasma, the fourth state, wasn't widely accepted until the mid-20th century. Despite being the most common state in the universe, what if we've already seen these new states before, but didn't recognize them? Today's labs generate massive amounts of data. A single quantum experiment can produce terabytes. More than entire departments generated in a year back in the 1990s. The sheer volume is overwhelming. Says one MIT physicist, "We're creating more data in a week than entire institutions once did in a year," which opens up a fascinating possibility. What if some of these exotic states have already been recorded but overlooked? Emerging patterns can hide in plain sight, dismissed as noise or error if they don't match expectations. This is no longer just speculation. At institutions like MIT, Stanford, and Google, researchers are now using advanced machine learning tools to reanalyze old data. These algorithms are trained to detect unknown phase transitions patterns human eyes may have missed or misclassified. "We're teaching AI to spot what we don't even know how to look for," says one data scientist. Involved in the effort, it's searching for the unknown unknowns. Another layer of intrigue comes from classified research. For years, agencies like DARPA funded work on unusual quantum phases and topological materials, often with an eye on defense applications. In computing, communication, or sensing, these projects have yielded major advances in superconductivity, metamaterials, and quantum tech, but much of their data remains undisclosed. If some of these exotic states were discovered in classified settings, would the public even know? Asks a physicist with past government project experience. It's not conspiracy, just the reality of how science often overlaps with national security. Now ask yourself this. If we've already made new kinds of matter by accident, how many more might be waiting in forgotten data files? The wave of discoveries continues to build. It's not just happening in one lab. Around the world, the floodgates have opened. In March 2025, researchers at Washington University announced a time quasicrystal with temporal structures that never repeat. They used microwave pulses to manipulate electron spins in diamond, creating a unique fingerprint in time. At Florida State University, physicists working with 5-layer, twisted, graphene-cooled, to near-absolute, zero-found quantum Hall liquids flowing through what they described as glaciers of pin charges. The system acted like both a solid and a liquid in 2023. Scientists at Nanjing University and UMass Amherst built a frustration device 2 layers of semiconductor material where electrons and holes moved in opposite directions at equal speeds. This gave rise to a Schirl-Bose liquid with magnetically ordered edge currents. At Cambridge, physicists created a 2D Bose glass refusing to thermalize, retaining memory in ways that challenged the expectations of statistical mechanics. Meanwhile, in 2021, researchers at the University of Konstanz observed liquid glass where particles moved freely, but their orientations remained locked, forming rigid, jammed clusters, and in Innsbruck, Austria, came final proof of supersolidity material keeping. Its solid shape, while generating quantized vortices, typical of frictionless superfluids, one after another. These discoveries are revealing behaviors in matter that physics never prepared us to expect.